So today we are going to talk about confidence intervals. I'm hopeful this is a topic that you all have at least some degree of familiarity with from prior statistics courses, and this is very closely related to what we've talked about in terms of hypothesis tests. It's basically just a different way for us to take the same data, make similar inferences, but the approach is somewhat different. And so we'll start by providing just an overview of what confidence intervals are. We'll contrast the development of confidence intervals or confidence limits versus the conduct of two-sided or one-sided hypothesis tests. And then we'll basically just demonstrate how confidence intervals can be developed across a variety of different contexts for various parameters of interest. As a reminder, assignment 2 is due at the end of the day on Friday, and I've got a little bit of feedback, so I won't have time to get you extensive feedback and grading on assignment 1, but generally speaking, the format and approach that most of you have utilized has been very good. Ultimately, I want to be able to clearly assess and follow your work, including steps in the processes, so that if you make a mistake, I can diagnose when and where that happened. And then I want to make sure that you determine both the statistical significance, so i.e. whether there's a meaningful relationship or difference or whatever the case may be. And then secondly, what those results mean from a practical perspective. And in addition to getting you feedback on assignment 1, I will also try to review the term paper topics by the end of the weekend, because we're looking to have the lit review due at the end of next week. So that's basically where we're going. And so at the end of today's lecture, hopefully you'll all be able to distinguish between hypothesis tests and confidence intervals or limits. And then from that, be able to calculate confidence intervals and limits for various parameters of interest. Okay. So if we think about this from a big picture perspective, hypothesis tests and confidence intervals are basically alternate ways of going about conducting or trying to determine inferences about some population parameters of interest based upon sample data that we've collected, okay? And so in the case of hypothesis tests, we basically want to make inferences about that population by determining how likely it is that a sample of data that we've collected would result in a particular value of a test statistic at some pre-specified confidence level of interest. So for example, you'll recall we generally conduct hypothesis tests such that we set out to disprove a null hypothesis that say the means between two samples are equal to one another, for example. And so if the null hypothesis is true and those samples are the same or not significantly different from one another, it would be very unlikely that we would observe very large or very small values of the t-test statistic using the sample data if in fact the null hypothesis is true. If the null hypothesis is not true, it's likely, or we're more likely to observe larger or smaller values depending upon the nature of the data, which would tend to provide evidence against the null hypothesis, obviously, and would give support to some alternate hypothesis that there's a difference. Whether that difference is in one direction or another would somewhat depend upon the context of the problem. And so we've talked about that extensively over the past few weeks. Now, in contrast with confidence intervals, what we're attempting to do is we're using the same sample data that we would use to conduct the hypothesis test, but we're using that data and some statistical and probabilistic theories to determine either an interval or a range of values or an upper or lower limit or boundary that the unknown population parameter that we're interested in will lie within some pre-specified level of confidence. So in this setting, we're basically taking the sample data based upon, in the case of tests of means, where the mean and what the variance of that test statistic is. We can then make inferences as to where that population parameter would lie on the basis of those intervals. And so we'll dig into this a little bit deeper, but the approach is analogous. It's just a slightly different perspective in terms of how we're working with those data. And so if we think about this from a big picture perspective, let's say we're trying to determine the value of some population parameter of interest. And that could be, let's say, the average number of fatalities after the helmet law change had occurred, or the mean speed after the speed limit increases in 2017. And so we can go out and collect samples of data, as we've done, many of you, for some of these research projects that we've referred to. And we can collect samples of data, and let's say we collect 20 samples. And if we just think about the underlying theories and probability and statistics, if we assume 95% confidence as our operating assumption here, we would assume that we would capture the actual mean population parameter roughly 95% of the time. And so as we see that demonstrated here, for each of these individual samples, those samples would have an associated mean and variance. And from that, we could determine a range that we would expect to see at whatever that pre-specified level of confidence is, whether it's 95% or 99%. And if we conduct repeated samples and those samples are drawn from this broader population, we would expect that those samples would generally include the true population parameter. So as you see here, we've got 16 samples. And when we construct limits about those 16 samples, we find that 15 out of 16 actually capture the true population mean here, okay? Now, sometimes, as we see with sample number 11 here, we just basically get unlucky and we draw a sample that just happens to be higher than normal, and that's just a function of random sampling. And for lack of a better description, we've been unlucky in that context. But As you can see here, as we conduct repeated samples here, we'll generally see that the vast majority of those will tend to capture that true population parameter of interest, okay? And so we can use that same rationale to try to investigate some of the research hypotheses that are of interest to us, okay? And the same general concept is applicable not just to tests of 1 and 2 samples, but we'll extend this for various types of regression frameworks and other settings within the context of this course as well. Okay, and so when we think about this, what we're basically doing is we're constructing limits based upon our sample data. So in the case of means, we're ultimately interested in drawing inferences about the mean of some population of interest, but since we're not able to observe that entire population, we're observing just a sample of that data. And so we're using X bar here as an estimate of mu, the population parameter that it corresponds to, okay? And so for any given sample that we take, there's going to be some level of error that's inherently associated with that sample. You know, most of the time we're probably not going to sample such that our sample mean is exactly equal to the population mean. And so as a consequence of that, through repeated samples, we'll have, you know, ranges of errors associated with those samples. And as we think about that, we'd like to be able to take our sample data and with some level of confidence construct a range of values that would actually capture that population mean a certain percentage of the time, again under the same assumption we've used in hypothesis testing, that the null hypothesis is true, or that in this case that our sample data are representative of that population data, okay? Or if we were comparing multiple samples, that those sample means were not significantly different from one another and their corresponding population parameters were not significantly different from one another. And we'll delve into that a little bit further as we move on here. But from a practical perspective, then what we're trying to do is construct a lower limit and an upper limit based upon that sample mean, as well as what we know in terms of statistical theory as it relates to either a Z statistic or a T statistic and the associated standard errors that are related to those statistics of interest, okay? And we'll delve into this in greater detail in the next few slides, but you'll start to see a few similar terms pop up here. So you'll notice we've got a critical Z value, we have the numerator from our Z statistic, we have the denominator from our Z statistic in the case of a one sample test of means with known variance. And so this is how we're approaching things conceptually, is we're trying to construct limits that would capture the true population parameter if the null is true some percentage of the time, with that percentage of the time that it's captured being our confidence level, okay? And so as a starting point, you're all familiar with this test statistic. As I had alluded to, this is for a one sample test of means. If we actually know what the population mean is that we're interested in comparing, and we know what the variance of that population is, now bearing in mind that we typically don't know that, but for demonstration purposes, we'd like to be able to take our sample data, and in this case, basically our sample mean, and that information we know about the variability of that parameter of interest, and based on the sample data, try to construct a range of values we would expect to observe for the population mean. And so what we're trying to do here then in concept is basically construct a confidence interval that would include that true population parameter, say 95% of the time, okay? And so we can think about that in terms of the standard normal table. If we think about our Z statistic, we know that if the null is true, we would see a value that falls within that range of plus or minus 1.96, 95% of the time, right? And so from that, we can basically rearrange this relationship in terms of mu and construct this such that it provides us with basically an upper and lower limit on mu that would contain that parameter 95% of the time based on our sample data, okay? And so just rearranging this in terms of mu, this then becomes we're just basically taking our standard error. We're multiplying that by both sides of the equation. We're then taking X bar, subtracting that from both sides of the inequality, and then we're multiplying everything by -1 to just get that in terms of mu. And so what we have then at the end of the day, a lower limit for that population parameter would simply be equal to our sample mean 1 minus 1.96 times sigma over the square root of n, okay? And likewise, an upper limit on that parameter would be X bar plus that same quantity, 1.96 times sigma over the square root of n. And so again, keeping in mind, we're basically operating under the assumption here that the null hypothesis is true. And so if that is in fact the case, then it's a relatively straightforward analogy for us to get from here, where we would reject the null hypothesis only if we observe values beyond that range of -1.96 to 1.96, to this setting, where based on our sample data, if that null hypothesis is true, we would expect that those limits from plus or minus 1.96 would contain that actual parameter 95% of the time, okay? So as you can see, we're addressing the same fundamental research question of interest, but we're doing it in a slightly different manner, okay? And so we can use that same approach if we wanted to construct an upper limit or a lower limit for mu. So we may have prior expectations such that if we go back to the motorcycle fatality example, we would expect that weakening the helmet law probably wouldn't make fatalities go down. It would probably make fatalities go up. And so we may be concerned with establishing a lower limit for the post-helmet law data and assessing whether or not our post-helmet law data included the same average number of fatalities from when before the law had been applied or changed. Or conversely, we could take data from the pre-helmet law period and we could construct an upper confidence limit there and assess whether or not the average number of fatalities after the helmet law change resulted in a rate that was greater than we would expect to see based upon sampling theory, based upon these limits we're going to construct, okay? So the approach is the exact same. In the case of the lower limit, we're just rearranging this. And so we're trying to determine whatever that smaller value is, that mu would be greater than 95% of the time. And so the setup here is similar to what you had seen on the preceding slide. The only principal difference here is that instead of 1.96, we now have 1.645, because that is the limit that corresponds to that 5% rather than the 2.5% on each side, okay? And so similarly, in the case of the upper limit, just rearranging that Z statistic, we would result in this same general setup here, except now we're constructing an upper limit for that parameter mu that we would expect the sample data would capture 95% of the time if in fact that null hypothesis were true, okay? And so if we want to simply generalize this, in the case of the confidence interval, so this would be analogous to a two-sided hypothesis test, we can construct a confidence interval at a level of confidence of 1 minus alpha. And so I don't know that we've explicitly mentioned this previously in the class, but our confidence level and our significance level are complementary to one another. So if we establish a significance level of 0.05 in a hypothesis testing scenario, that would be analogous to a 0.95 or a 95% confidence interval or limit. And so to that end, if in the case of a two-sided interval, we would be interested in whatever that two-sided critical value of the Z statistic would be. And we would want to select a value of Z such that each of those tails would comprise alpha over 2, or half of our significance level. So in our common 95% confidence level, we'd have 2.5% on each side of that distribution. And so generally speaking, our limits would be whatever our sample mean is plus or minus that corresponding critical Z value times the standard error associated with that test statistic, which in this case would just be sigma over the square root of n, okay? And then similarly, in the case of our confidence limits, the lower limit would simply be X bar minus, in this case, since we're concerned with just one side of that distribution, we would use Z sub alpha instead of alpha over 2 times our same quantity sigma over the square root of n. And similarly, the upper limit in this case would be the sample mean plus that same quantity, okay? All right, and so the easiest way to work through this is probably simply by revisiting some of the hypothesis tests that we had conducted in previous lectures, and now in this case, instead conducting those as basically confidence interval construction, okay? And so in this case, we're going to compare a one sample z-test to the development of a hypothesis test procedure. And so you may recall in previous lectures, we've examined whether or not motorcycle fatalities had increased as a consequence of Michigan's helmet law change that occurred now roughly 10 years ago. And so you may recall from those tests, we had collected sample data that showed after the helmet law was weakened, we had experienced an average of just under 123 fatalities per year. And when compared to the few years prior to the helmet law being weakened, we had observed 106.5 fatalities per year. And our historical data had suggested a standard deviation of 9.2 fatalities per year. And we had worked with 6 years of data immediately following that helmet law change. And so our calculated test statistic here was 4.30. We presumed in this case that we would see a large positive number, so we would conduct this as a one-sided hypothesis test. Ergo, our critical value would be 1.645. And of course, 4.3 is significantly larger than that associated critical value. And as a consequence, we would then reject the null hypothesis in this case, okay? So if we revisit that same question from a confidence interval perspective, we would be interested in this circumstance in determining, using that sample data from the period after the helmet law was weakened, we could construct a lower limit, okay? And so if our null hypothesis is true and that helmet law didn't have any meaningful impact, we would expect that that confidence limit would actually include whatever that pre-helmet law fatality rate of 106.5 was in this case, okay? And so to that end, we go back to our general setup for the confidence limit determination here. And just plugging in the sample data that we had collected previously, we know that our average number of crashes based on the sample data was 122.67. Our corresponding critical value was 1.645. Our standard deviation and sample size as shown in the hypothesis test to the left. And so this basically tells us that that lower limit we would expect to see for mu based upon the sample data that we've collected. If we assume the null hypothesis is true, we would see values that are greater than or equal to 116.49 95% of the time, okay? Now, as it turns out, that 106.5 average we saw prior to the helmet law change is significantly below that limit. And so what that means, if in fact the helmet law had had no impact, it would be highly unlikely that we would see that low of a value for the population parameter based on the sample data we've collected for the post-legislative change period, okay? Ergo, the pre-law change limit is below, and we would come to the same conclusion ultimately then. We would reject the null hypothesis, okay? And so at this point, I just want to make sure that we're all on the same page in terms of the setup, because we're going to go through a number of similar examples. So if you could just give me the thumbs up or a wave or whatever the case may be, just to indicate that you're with me now, that would be very much appreciated. And if you have any questions as we work through this, feel free to type those into the chat box, but otherwise it looks like we are probably good to continue on at this point, okay? All right, And so we had just presented a demonstration of confidence interval or limit construction for cases where we're interested in the mean value, but our variance is known to us. Now, as I've said previously, for nearly every practical purpose, we're not going to actually know what that population variance is. And so in that scenario, the one substantive difference is, well, I guess we can say there's two substantive differences. First and foremost, we don't have an actual value for sigma, and so we would need to estimate sigma based on our sample data as shown by S. And rather than using our standard normal table, we don't have quite the same level of confidence and certainty given that our sample sizes are generally smaller in this case. And so instead of using the Z distribution, we're using the T distribution. And as you may recall from prior lectures, the primary difference between the Z and T distributions is that the T distribution is less peaked in the middle. So we'd have fewer values that are near the center or near zero for that test statistic if the null is true. And we'd have a slightly larger number of observations out in the extreme value. So that distribution would tend to have larger tails, fatter tails, as the case may be. Okay. And so in any case, the setup is analogous here. So these limits are exactly as we saw for the case of the Z-test, with the only differences being we now see T's instead of Z's, and we now see S's instead of sigmas, okay? The one other difference that's important to note here is that the shape of that T distribution, of course, is going to depend upon the number of degrees of freedom we have to work with. And so that's why we see the n-1 here when we're dealing with a one sample test, okay? And so confidence interval setup is as we see right here. And similarly, if we're concerned with just one side of that distribution, or if we have a prior expectation that our effects, if the null were not true, would be in one direction or the other, we could work with lower limits or upper limits as we had detailed in the preceding case, where the only difference between these confidence limits and the confidence intervals are that we're replacing alpha over 2 with alpha because we're focused just on one side or the other of that respective distribution. And then everything else is basically analogous, okay? And so we'll return to the same scenario we had investigated previously, except now working with the one sample T. And so basically everything's identical to what we'd seen in the case of the Z-test, except you may recall, if we looked at the variability in data after the Helmut law change, we actually saw more variability in fatality counts from year to year. And so our standard deviation S is a bit larger than sigma was for the pre-Helmut law change period. Nonetheless, our test statistic is still quite large at 3.06 in this context, okay? And so we would compare that to the associated critical value. In this case, if we're assuming a one-sided test, we would go to T of 0.05. We have a sample of size 6. And so with 5 degrees of freedom, our critical value is then 2.015. We compare those to one another and, of course, come to the conclusion that we should reject the null hypothesis and conclude that the Helmut law did, in fact, contribute to an increase in motorcycle fatalities, okay? We could address that same question using the sample data from after the Helmut law change and constructing a lower limit based on those data and assessing whether or not that pre-change fatality number fell within, or in this case, above that limit. And so again, the approach here is similar to what we had seen in the case of the Z-test. We again are taking our post-Helmut law fatality average of 122.7, the same critical t-value outlined previously with 5 degrees of freedom at 0.05 for our significance level is 2.015. Our sample standard deviation and our sample size are shown here, and so our lower limit in this case is 112.01. We compare that 112.01 to the 106.5, and since this is a lower limit, again, we would expect that if the null were true, that 112.01 would capture the actual value we're comparing against, but in this case, the 106.5 actually falls below that lower limit. Consequently, we would come to the same conclusion as we would in the case of the hypothesis test, and we would then reject the null hypothesis. Okay? So the setup here is just as we've seen previously, and we can continue to extend this beyond the 1 sample cases to the 2 sample cases as well. And so we've previously went through and discussed a number of different tests by which we could compare differences between the means of 2 populations. And so the first of those cases, if we had an instance where the variances of samples 1 and 2 were known to us, we could conduct the 2 sample z-test, which you see illustrated here. Again, as a reminder, we're generally testing whether or not there's any difference whatsoever in these population parameters. And so in the numerator, this term would reduce to 0. And we're left with the difference in the sample means divided by the square root of the population variance over its associated sample size for the first sample, and the variance of the second population divided by the size of that sample as well. Okay? Alternately, we could construct a confidence interval around that difference in means, and this is done just as we had walked through in the initial example. We're just rearranging this term, and we'd be setting the z value equal to its corresponding critical value in the case of a 2-sided test, or a confidence interval in this case. That would be z alpha over 2. And then we just bring that standard error term over to the other side of the equation, and this would give us a similar limit to work with. Okay? And continuing on, as we've talked about previously, we typically wouldn't know the variance of any 1 population, let alone the variance of 2 populations. And so we'd be left with the circumstance such that we have variances that are equal to one another but unknown. And so in that instance, we would be relying on student's t-test. And so the setup here is analogous, except since we're assuming those variances are equal to one another, we pull that out, estimate a pooled variance. Everything else is virtually identical, with the one caveat there that we're using the sample variances as opposed to the population variances, since those are unknown to us. And the analogous confidence interval set up similarly is exactly as we'd see above, except now in this case, our t-value is going to have n-1 degrees of freedom for each of those individual samples, as a reminder. So sample 1 would have n1 minus 1 degrees of freedom. Sample 2 would have n2 minus 1 degrees of freedom. And taken in summation, then our total degrees of freedom in this case would be n1 plus n2 minus 2. And everything else is as discussed previously. Okay? And then the third case we talked about, at least as it relates to our parametric tests of interest, if our variances are unknown and we're also have demonstrated that they're unequal to one another, we would use Welch's t-test instead of students. And so the only difference here is that since those variances are not equal to one another, we're no longer pooling them as we had in students' case, but we're applying each of the individual variances over its corresponding sample size. And so this is directly analogous, as you'll see here, to the 2 sample Z. And similarly, we'd see an analogy here with respect to the preceding confidence intervals, okay? Now, the one difference here that we should restate is that instead of having n1 plus n2 minus 2 degrees of freedom, we'd find that would only be the case if, in fact, our variances were equal to one another within those 2 samples. And so in this case, we would calculate mu, which is our degrees of freedom, and I've omitted the long form calculation here, but you may recall that's simply a weighted average of the degrees of freedom based upon the differences in the variances of the 2 samples and their associated sample sizes. Okay? And so we'll now work through a few additional examples using the same Helmut Law data we had introduced previously. So first of all, we'll work through students' t-test, just as we had previously. And so our test statistics are ultimately similar here. You'll notice a subtle difference because we've used a slightly larger analysis period here. Instead of 106, we see actually an average of 104.17 for the 6 years of data immediately preceding the helmet law change. We see the same 122.67 for the after period. Again, we're just testing whether there's any difference here, so this term drops out. Our pooled variance is 119.22, and each of our samples are of size 6, okay? We compare that test statistic to the corresponding critical value, and I've noted here simply that we're conducting this as a two-sided test. Now, going in, we had a prior expectation that this test statistic would tend to be negative, but I'm doing this largely just to demonstrate an analogous condition where we'd look at confidence intervals versus confidence limits. And so in this case, comparing our negative 2.93 to plus or minus 2.228, since we're below that value, we would then come to the conclusion, as we've done with each of the preceding tests, that we should reject the null hypothesis, and we'd find that there was a significant difference in fatalities between the two periods, okay? And so we can do the same thing in terms of establishing a confidence interval. And so the equation here, apologies, it's a bit large, so it's running across two lines, but we're just rearranging the preceding t-statistic that we had calculated in the case of students test. And so plugging in our corresponding values, and the one difference here is that critical value of 2.228 is now plugged directly into our corresponding confidence interval equation. And this range covers negative 32.54 to negative 4.45. And so what that means in practical terms is that 95% of the time, our population parameter based upon this sample data would fall somewhere within these respective bounds, okay? And so if we want to think about this in terms of our underlying hypotheses, what was our hypothesized difference between mu1 and mu2? Under the null again, anybody? Yeah, thank you, Nishal. So we assume that a difference of 0, right? And so all we're doing in the two-sided interval, in the confidence interval case, is we're assessing whether or not that interval includes 0. If it includes 0, we don't have sufficient evidence to reject the null hypothesis. But if 0 falls outside of that range, it basically tells us that our sample is generally incompatible with that underlying hypothesis based upon the confidence interval we've established here. And so consequently, we are in this case then rejecting the null once again. We return to Welch's T, and just as we had done previously, we can plug in our sample data that were collected previously. I've talked through ad nauseum what these corresponding statistics represent in terms of the fatalities before and after the helmet law change. In the case of Welch's test, we would need to calculate our corresponding degrees of freedom in order to determine that 2.306. So we'd have just the 8 degrees of freedom given our differences in the sample sizes here. And so in this context, then our confidence interval would range from negative 33.04 to negative 3.96. And so the one thing you'll notice here is that that limit has now gotten slightly larger than it was previously. And this is an important point to bring up because if we think about how we've generally structured our hypothesis test previously, we would select our critical value in part based upon the degrees of freedom, and the fewer degrees of freedom we have to work with, the more conservative we'd want to be from a hypothesis testing perspective. And so to that end, if we have fewer degrees of freedom, we want to establish a larger critical value as a consequence, okay? When we construct confidence intervals, we're going to use the exact same rationale, basically. If we have smaller sample sizes and or if we have fewer degrees of freedom available to us, we want to construct those intervals such that they're larger and would be inclusive of a broader range of values because we don't have the same level of precision given those differences. And so as a consequence, that's why we see a slightly larger range in the case of Welch's versus T, and that will happen again as compared to students T. And that's going to happen anytime our variances are not equal to one another, basically, okay? And so in this case, though, we'll still find that that confidence interval does not include 0. And since it does not include 0, we're then going to reject the null and again claim that we do have a difference in this case. Okay. All right. I'm just going to briefly go through a few examples here. So beyond the test of means that we've talked about previously, we can basically use any of the hypothesis tests we've talked about up to this point, and we can rearrange the nature of those equations such that we can convert the hypothesis test statistic to an equivalent confidence interval or confidence limit, okay? And so, for example, if we're conducting a one sample test of proportions, in this case, you may recall our test statistic, we would simply take our difference between our sample proportion, p hat, and some corresponding value of interest, p naught, and we would take that ratio over the corresponding standard error, which would be p hat times 1 minus p hat, that whole quantity, over n, and that is how we would construct the confidence interval in this case. Now, there's one important point that I should note here, and we talked about this during the last lecture. If we looked at the analogous hypothesis test in this case, that denominator would have p naught times 1 minus p naught. And in this case, for the confidence interval, instead of p naught, which we're assuming is a known value based on our population, in this case, we're making inferences using exclusively the sample data. And so we would construct that interval using p hat and 1 minus p hat. And then we would compare our p naught value, whatever that reference proportion of interest would be. And so we used a value of 0.5, I think, in the preceding example. And so there's a subtle difference there, but otherwise the setup is completely analogous here, okay? So we can use this approach for making inferences about population proportions. Likewise, if we think back to our one sample test of variance, you may recall that was a chi-squared statistic. And all we were doing in that case is we were attempting to make inferences about our sample variance as compared to some population variance of interest. And that test statistic was just n minus 1 times s squared over sigma squared, okay? And so simply rearranging our equation in this case, we can construct confidence limits by plugging in the corresponding chi-squared test statistic. Now keep in mind, this is a test that was set up as a test of ratios of variances. So the look of this is slightly different as compared to some of our preceding examples, but the setup ultimately is the same here. And so if we know our sample size, our sample variance, we pull the corresponding critical values from our chi-square table, and then we would assess whether or not this interval included whatever that population variance sigma squared was equal to, okay? Similarly, any of the other tests that we've talked about, so in the case of the paired t-test, we would look at constructing an interval using sample data for our mean difference. Keep in mind here in this scenario, since we're looking at pairs of observations across the two samples, our degrees of freedom for that test statistic would have been equal to just n minus 1, where n is the number of pairs across those two samples. So we're basically having our sample size or our degrees of freedom, as it were, here. And this would be the standard deviation of those differences divided by, again, the square root of the number of differences that we're observing, okay? And then likewise, we talked about a two sample test of proportions previously. And so we're just rearranging that corresponding test statistic. So the numerator in that equation would have been p1 hat minus p2 hat, all divided by the square root of the standard error quantity. And so you'll recall in that case, we had demonstrated that the test statistic followed a standard normal distribution. And so we're back to using a critical Z value here, Z alpha over 2 for the case of a confidence interval. And as just an aside here, if we were interested in just one side here, we'd be constructing a confidence limit. So the setup would be the same. And we just have alpha instead of alpha over 2, and then either a plus or minus sign, depending upon if we were constructing an upper or lower limit. Okay. And then lastly, our F-test of variances, as we see down at the bottom here, you'll recall that's the simplest test that we've talked about up to this point. And so we just basically take the variance of the first sample divided by the variance of the second sample. And keep in mind, in this case, the F tables are a bit more complicated because we have a different set of tables for each corresponding value of alpha. And so we would need to take that into account then as we determine our corresponding values for F here, which we would use to construct the limits, which we would then compare to the ratio of the population variances. And as you may recall here, this test is somewhat different from the others in that we would assume that this ratio would be equal to 1. And so we'd be assessing whether or not this limit included the value of 1 instead of the value of 0, for example. Okay. All right. So that gave you a relatively concise overview to confidence intervals, how they work, and the natural analogy we see here between confidence intervals and hypothesis test procedures. Okay. So at this point, I think we are essentially through all of the 1 sample and 2 sample tests of interest. We'll begin talking about tests that involve more than 2 samples next week, and that leads us into a concept called analysis of variance, or ANOVA. I should note the Mannering textbook is very much lacking in respect to this content, and so as a consequence, I'll be providing links to some supplementary resources that will help you to that end. And then assignment 2 is due this week, and the term paper literature review is due next week, okay? And so that wraps up my content for today. However, I have a few additional items I'm going to cover here really quickly.